Professor at the Technical University of Valencia in Spain. And they invited me today to follow up on some lectures. I already had the pleasure to be here last October. I see no faces everywhere. I have some things waiting for you later from briefings. And so basically today and tomorrow I'm going to cover 4 topics. The first topic is, apart from an introduction to, I will introduce to you our group research activities, and then I will discuss about the ecosystem of photonic integration. What is photonic integration? Which is the current state of the art? And last but not least, which is quite important, which are the things that are preventing this ecosystem of photonic integration to get widely extended and widely adopted by many others. That will be the first session today. I hope that we can do that in the time that we have allocated for the first session. The second session today. Please ask. Yes.
Уважаемые коллеги, перевод нужен дословный или как мы в прошлый раз работали? Если непонятны какие-то отдельные слова, фразы, темы, мы останавливаемся и разбираем каждый кусочек по отдельности на русском языке. Либо мы идем на английском преимущественно. Если какие-то вопросы возникают, понимаете, как я не перевожу и объясняю. Какая? Преимущественно на английском. Ну, хорошо, у вас английский все хорошо.
Лучше второй вариант.
Если какие-то вопросы будут по поводу перевода, по поводу объяснения определений, именно принципов работы, вы поднимаете руки, спрашиваете, буду останавливаться, разбирать, хорошо? Yeah, let's go. As we did previously, I was to talk in English. If they don't have any questions, let's ask them to raise the hand and all this. Yeah, no, just like
So, as I was saying, this will be the first session today, and then in the second session I will cover a topic which is microwave photonics, in particular the use of photonic integrated circuits in the topic of microwave photonics. Tomorrow we will have 2 other sessions, and I will cover biophotonics and infrared photonics. I think that all this was said already by Ian. Okay, so let me start with a presentation of the research laboratories I'm working in. So our research laboratories are now called Photonic Research Labs, are part of Research Institute in the Technical University of Valencia. And basically our mission is to educate young professionals in optics and photonics. And that can be done through research programs, through contract with universities, and through contract with other companies, and as well through master and PhD programs in the same university. We've been doing that, well, not me, but the most senior people in the group nearly 25 years. And basically we are organizing several research areas like microwave photonics, fiber-based photonic devices, and photonic integrated circuits. I am the one leading photonic integrated circuits. These areas are not totally separated, because some of the technologies that we do in some area, we combine with others to get synergies, right? So you will see later on in the second session how we are doing that of microwave photonics with photonic integrated circuits, okay? And to summarize rapidly, our laboratory is an optical telecommunication laboratory. That means that we have equipment which is able to generate and test signals, digital signals up to 40 gigabits per second, and analog RF signals up to 50 gigahertz frequency. And inside the lab we also have some, let's say, singular facilities which are not the regular requirements one can buy in telecom instrumentation vendors, but also this fiber Bragg rating fabrication facility. I'll show you some slides later on, and the equipment or the setups to be able to test the photonic integrated circuits as they come from the foundry without any packaging, without any fiber. Okay, so this is a summary of the requirement. I don't know if it is worth to go through all of it. Nearly anything that you can imagine you need for an optical fiber telecom test, either RF signals or photonic signals, you can find it in our labs. Lasers, optical spectrum analyzers, network analyzers, etc. As I said, we have one facility to make fiber Bragg ratings, which maybe most of you know. It is a regular or sort of device which is written into a regular or a special fiber, into the core of a special fiber. And we can do that on standard single mode fibers, multi-mode fibers, polarization maintaining fibers, or even microstructured fibers and multi-core fibers. And last singular thing is that we have the setups to measure the photonic integrated circuits, to test the photonic integrated circuits that come out from the fab without any package, any fiber connection, as I said. So you can see here an enlarged picture of a photonic integrated circuit, an optical fiber which is coming from the right-hand side, and then some needles which are used to probe the optoelectronic parts of these photonic integrated circuits. To do all these, you need translation stages, which I know that some of you are familiar with, and vision systems, basically. Okay? So we have now 3 of these setups for edge coupling. That means injecting and collecting the light through the facets of the optical chip. This is the chip injecting and collecting. And the other one, which is for vertical coupling, which is injecting the light vertically and collecting it vertically as well. Okay? And we are, right now, because of the projects I'm going to show you, we are doubling the space of our lab. And then we will have a dedicated area for photonic integrated circuits. So, from our group, we spun out 3 companies. The first was PLC Photonics, which I mainly founded with others, and which is devoted to photonic integrated circuits, from design to fabrication, packaging, etc. It's a fabless company. That means that we actually do not do fabrication ourselves. We don't have facilities to fabricate the circuits, but we resort to other third parties. Second company that our researchers in the group spun out is CalSense. It's, well, the name may be a little bit self-explicative sense because it uses fiber devices for the sensing application. Okay, basically fiber Bragg ratings, and they have also patents for high temperature fiber Bragg ratings for sensing high temperature environments. And the last company we started, or other researchers of the group started this last summer. It's Epoxy Engineering. This is an instrumentation company. Since we have been working in RF photonics for many years, we knew which instrumentation was on the market and which were the features this instrumentation was lacking. And basically, the researchers in the group developed their own instrumentation for their own use, and later on they decided to make it commercial. So it is a module that can be added to the main vendors, Agilent, Rose Schwartz, and Advantest, and it incorporates an electrical vector analyzer, optical vector analyzer to electrical vector analyzer. Okay, that's it.
Кто-то что-то понял?
Установка можно вернуться? Нет.
Даня просит к установкам вернуться.
Или потом детально можно, потом по установкам. Там некоторые части вопросы.
Завтра.
Because that's more same technology and try to couple in, couple out light and need to make clear our reports. You can ask questions right now, rotate or later.
When you want.
But let's do it right now, just
Which is
discussion. Probably in this case Pascal will understand what we want and what we need to. So
Вот там в данном случае приведен тег поддержка, да? Правильно понимаю? То есть, он интегрирован в установку.
The question was that.
Yes, there is a
temperature.
There's a temperature component, yes.
It is integrated into equipment or like.
Well, it's a separate piece of equipment that we make it work together. Basically, I don't know if you can see it. This thing here is a copper chunk that you can see here. It's copper, okay, and the Peltier cell is sitting below with a thermal glue on both sides, and then there is a thermistor going in somewhere, and then it is controlled by the thing. And you need to do that in nearly all the experiments because the photonic integrated circuits, the refracting index is temperature dependent, you know it. So.
And you use in your alignment also, or just for investigation?
No, we usually turn it on when we go to the lab, and it's turned on until we finish. So because it takes some time to. Not long. It is good that they stop me, or that you stop me when you have questions for me not to be too obvious.
Tomorrow we will show the
Okay, fantastic. Okay, great. Great. So last part of our research group introduction is I discussed with Juliana. Okay, tell us which are the projects you are working. So we just asked to see if there are mutual interests. So this one is maybe the most related to what I'm going to talk in the second session today, and it is a big project. Europe has the European Research Council, which basically funds excellency research, and this is a personal grant that our lead senior researcher, Professor got with the support of some of us. Basically, the project addresses the challenges that exist between two types of telecommunication network. Okay, so basically the wireless telecommunication network and the backhaul telecommunication network, which is mostly fiber optic based. Okay, so a long time there is always an increasing demand of capacity in the wireless network, whereas that is also true in the backhaul network. And there are issues in interfacing, in transforming the signals from the wireless into the fiber optic network. This project addresses that challenge, okay? And that it will use microwave photonics, which now maybe you don't know what it is, or you know it, but I will later on develop it a little bit better. And it basically proposes the use of photonic integrated circuits to do the interface between the wireless world and the fiber optic network in the background. Up to now, and we will see it also in some parts of the next session, this has been done more or less with, let's say, limited functionality photonic integrated circuits, and the proposal is a little bit more ambitious because it wants to propose chips which are actually programmable, and they can do different functions at the same time, not one chip, one function. Okay, we'll see something about it later. This is one of our big projects, and yeah.
Will you explain what exactly limited function?
Yes, I will explain later on which circuits have only some functions and how to turn them into programmable devices, okay? Or how are we willing to do that. Then another large project that this lead researcher in our group got is InnoSpace, which basically addresses challenges in the same area in interfacing wireless and fiber networks. But in this case, it addresses from a fiber perspective instead of from a chip perspective, from a fiber perspective, because of course there are things that are harder to do in a photonic integrated circuit, and there are new types of fibers which are good for that. And in this case, these are the fibers which have multiple cores. Okay, not a fiber with a single core, but with multiple cores. Basically, with multiple space lanes through the fiber, okay, space division multiplexing. And they are proposing novel alternatives to do photonic processing, not only distributing the signals, but also some processing by using different special fibers. Then another one, which is also on the same topic, it is closer to a final application. This, I would say, these two are more like, say, leading edge research, fundamental research, leading edge research. And this one is closer to the final application, because actually it's proposing to do some application using, again, space division multiplexing, but in this case for a beamformer in the gate A bands. Okay. There is also another one which is an interesting mechanism for young researchers, and that maybe you should stay tuned to this type of project, because these ones are called innovative training networks. Okay? So in this project, the main focus is not the research. It has a lot of weight. The research has a lot of weight, but the training has even more weight than the research. And these are networks that are built around the different partners. In this case, for distributed optical fiber sensors. Okay? We have been applying for photonic integrated circuits without success until now, but we will keep doing so. And the good thing of this is that job positions are offered 1 or 2 per institution, so you can see how many job positions, more or less half of them offer 1 or 2 positions for 36 months. So stay tuned. Most of them publish the job positions in a web which is called Euraccess. Okay. Yes, I don't remember by heart, but Access.eu or something similar. Okay. So most of the job positions for the projects and for these training networks are here. Okay. Then there is another comparatively smaller project. I have discussed or showed 2 types of them, or 3 types of them. More leading edge research or fundamental research, then more close to industry research, education oriented research. And this one is market oriented research, in the sense that there are technologies that have been developed, how to get access to those technologies by others. So research project developed technologies, in this case photonic integrated circuit manufacturing with multi-project wafers. Later I will tell you what is that, and how to get access to that if I am not very well aware of the ecosystem, but I feel that I need the photonic integrated circuit. So this is one of these projects, and there are different application centers that you can contact if you are interested in using the photonic integrated circuit ecosystem. You can contact any of them. I mean, geographical proximity is not a must. I mean, you can contact us in Spain or someone in Okay, then this one belongs to VLC Photonics, our spin-off company, and this is related to the first talk I will give tomorrow. Tomorrow I will talk about biophotonics, okay? And the biophotonics is usually done with visible wavelengths, with light which is visible. Basically because tissue and all the bio parts of our body are not harmed by visible light. So visible light is convenient because it will not destroy the samples, okay? We are used to visible light. And if you want to do visible light with, for instance, photonic integrated circuits, well, you will usually resort to a material some of you are already familiar with as well, which is silicon nitride. So this project aims to establish a silicon nitride fabrication, pilot line for fabrication. So where you can have all the ingredients that you require in a biosensor, not only the photonic integrated circuits, but many other things like the fluidics, the electronic readout, etc., etc. We will talk about this tomorrow. And then this is one of our national projects in which we are trying to expand the use of silicon nitride to longer wavelengths, wavelengths which are above the near infrared. Typically the telecom wavelength is 155, which is called the C band of the optical fibers. And we're trying to go above, and this is related to the last talk of tomorrow, because basically at longer wavelengths there are unique wavelengths where you can distinguish some molecules versus others. So basically there are what is called fingerprint regions, where if you find something in that wavelength, you know it is maybe CO2. Okay? And in that sense, what I'm telling is actually you want to distinguish wavelengths in a wavelength range which is longer than the telecom. So there are material challenges that I'll present tomorrow, and there are other challenges, which is how do you select the wavelengths in this range. So we are, in fact, we have patented this thing, and maybe if there is still time tomorrow after the lecture, I can talk about it. And it is a spectrometer to basically self-reference spectrometer to sensing the infrared. So that was a good presentation.
Yeah,
Could you explain again about blue space?
Yes. Yes. Okay, this blue space project. Okay. Well, the explanation here is not, it is quite abstract. In fact, it's the abstract of the website. The project starts today. They are on the kickoff meeting right now in Eindhoven, in the Netherlands. And basically, it's a project to do beamforming efficiently. Beamforming is a technique used in antennas for you to create a beam and to steer it in a given direction. Okay? Not only for defense applications like radars, but also for civil applications like, I don't know, 5G and those things, okay? Basically, you have an array of antennas, and then you feed them in phase, or with a given phase relation, and that creates a beam, and that beam can be steered to that user, or to that user, or to that user, okay? This can be done electronically. But it is already recognized from many years ago that the best thing is to use photonic techniques to do those things. Okay? Either you can do with photonic integrated circuits, which has been already demonstrated, and there are some companies that are trying to commercialize those photonic integrated circuits for beamforming, or you can use, again, multi-core fibers. So this project is the one that is trying to use multi-core fibers, and it's starting like today. So I cannot tell more because there's no more yet. More or less? Yeah. Any other
As
questions?
advertisement, I would like to mention that we are looking for a joint project with the University of Valencia, and probably we will send somebody there to carry out research projects. Interesting for us, interesting for Paskal as well. We'll probably keep it in your mind.
I have a question. One project about spectrometers. Now properties of spectrometers is not enough? Or
That's a good question. Okay. Properties of bulk spectrometers are very good enough. They are like this or this, okay? And actually what we want to do is to bring, and they are very good because you can reconfigure many things, the sweep range, the resolution, many things, and that is done mechanically, typically it's done mechanically. We want to bring these reconfiguration capabilities into a photonic integrated circuits, acknowledging that we are not going to make the same resolution than the regular FTIRs, okay? But for some applications, it is enough to resolve the spectrum with not that much resolution. Okay?
Okay, do you ask for translation?
Yes.
На данный момент спектрометр работает в некоторых предметах, если есть и с интерфейсным решением. Если достаточно каких-то применений, например, на телефон на 55 разрешения нанометров в полноценном диапазоне от 0,4 до 0,6, то спектрометр в этом диапазоне работает. В другом диапазоне они уже не работают. То есть ограниченный диапазон. Они идут дальше. You are going 155 and drop.
Yeah, that is the wavelength range where we want to operate. That doesn't mean that it covers the full range. Okay?
Да, в том числе для биологических применений, когда время волн больше 1,6 до 2 микрон в том числе, там уже начинают появляться явления, поглощения или наоборот флуоресценция отдельных полей, что используется для биологических применений. Это так называемый fingerprint отпечаток пальца, ну, если дословно переводить. Мы благодаря вот этим пикам поглощения и излучения флуоресценции можем однозначно определить состав, какая молекула, какой элемент переизлучает и поглощает. То есть, раз мы занимаемся биосенсорами, несколько раз пытались их передавать на спектр. Но мы все с вами знаем, что в спектр может быть температура и давление. В данном случае мы однозначно с помощью пиков поглощения поражения, пиков поглощения флуоресценции можем определить, что находится в данный момент. That's for biophotonics applications, as it was mentioned previously.
Now, this one is more for, should we say, chemical analysis, because for that wavelength range is mostly chemical analysis. Although you can do some biophotonic assays also in that wavelength range.
Получается, что если спектрометр в другом диапазоне работает, то у них много широкого, то есть 1,5-4 микрона.
To make clear, do you try to invite, do you try to develop a spectrometer of your full range from 1.5 to?
That is the wavelength range operation. With waveguides, it is quite hard. With waveguides, it is quite hard to do that because it is difficult to preserve the single mode condition on that huge wavelength range. Okay.
In this case, you also develop new devices which are able to work with this.
Yes, we are.
Strange.
Okay. We have a silicon nitride technology, and we are trying to see which are. We already know which are the things that prevent their use in longer wavelengths above 2 or 4 microns. And then and I'll show you tomorrow. And then in those regions, there are, like, for instance, glucose sensing is done in between 2.1 and 2.3. Okay, so actually you don't need a spectrometer for all the range, you just need it there. Okay, so there are areas in which, depending on the application, you can choose your design or design.
То есть они делают небольшие компактные спектрометры в каких-то заданных диапазонах. И для различных диапазонов отличается количество применений. Если словно переводить, то для тестирования глюкозы нужны минимум 2,2 десятых микрона. И получается, что спектрометр должен работать в этом диапазоне дальше не достаточно. Да, достаточно. Для каких-то частных применений.
То есть получается идет создание нескольких спектрокартометров, предназначенных для различных целей, которые работают на различных глубинах.
Практически каждый раз, меняя дизайн, вы можете волны, которые вы детектировать, и заданные точно. As just a general introduction, big spectral analyzer is like this big machine that is 7 kilograms, probably that. It's really hard to apply it in your I'll switch to Russian. Я, конечно, сейчас общем, спектроанализатор — это, в принципе, большой такой блок, который не всегда удобно притаскивать с собой для каких-то применений уже в поле полевых условий, для каких-то небольших датчиков. Когда мы говорим, разрабатываем системы, которые носит человек на руке, нужно измерение, там, буквально цифры некоторого набора длинного, нужна компактность, все требования предустроены компактность, специальная компактность. Чтобы это все было встраиваемо, чтобы это все передавало информацию, чтобы это было всегда с человеком, чтобы сократить вес космонавтов в применениях для космоса, для аэрокосмических применений, так сказать, корректно. И получается, здесь у меня цель такая, создать компактное устройство, компактный спектрализатор для конкретных применений на чипе, на основе фотонных. Если до этого весит 7 килограмм, то после минимализации это чип, который размещается на пальце, Just for general introduction, what is digital spectrometer?
Okay. Thank you. Any other questions? Okay. Next one. So, second part of this first session is to describe what is generic integration technology and multi-project wafers. I already did that in October, but I will refresh. And then I will present which things are roadblocking or preventing the wider use of this technology. Okay? So this is the outline of the second part. Basically, it is divided into 3 main parts. A part is from the introduction, roadblock, evolution, and conclusion. Okay? So, what does fabless mean? Does anyone of you know what fabless means?
You don't need a fab.
You know it? No?
No.
Good. Roman said something.
Maybe you don't need a fab to create your device.
Your device, okay? Yes, fabless means you don't actually own the manufacturing capability. Okay? That means fabless, without a fab. Okay? Fabless. Okay, so let's talk first, before diving into photonics, let's talk first about electronics, which is basically, again, this is very helpful, okay? This electronics, okay? Electronics, as we know it today, started last century in the 50s, and it was done by companies which were called and are still called IDM. IDM is Integrated Device Manufacturer, which is a company that actually owns the manufacturing factory. They have the machines, they develop the processes to fabricate the circuits, they fabricate the circuits, they have their own software tools to design the circuits, they package the circuits, they sell the circuits, etc., etc. Basically, it's one company that does everything from the bottom up to the top, okay? This is a long time in electronics for several reasons. I may show some of them later on, but now it's not important. Disaggregated into different types of organizations. In companies that, for instance, companies realized that the manufacturing tools were the same for IBM and AT&T. So basically they said, okay, we're going to get out of this company and I'm going to build my company of manufacturing machines, okay? And then some other companies realized that the processes that AT&T and IBM were using were more or less the same, so they said, okay, I buy the machines and I do the processes for both. Okay, basically it was like a disaggregation of functions in the different companies. Also, the people that were doing the software for IBM, they said, I could sell the software as well to AT&T. So actually they create their own company and they do software to sell to everyone. So basically that is the disaggregation, okay? So we have...
Sorry to interrupt, I need to go and ask, did they understand something because the job a bit fast?
Oh, sorry.
For me everything is okay, but I need to make clear that everything is okay for them. Понятно все или надо что-то переводить, остановиться просто сейчас? Нормальный темп разговора, просить чуть-чуть помогли. Okay, they probably ask you to talk slowly.
Yes, sorry. In fact, I did this presentation in the USA, this part, and I had 20 minutes, but here today I don't have 20 minutes, and I forgot that.
In case
No, it's okay.
We can do it for 5
we do this, and if it is time, okay, we can do the break. Okay. So what I was trying to say is, I'll try to say it slower, is these companies broke apart into pieces. Why? Because, okay, these guys have had the manufacturing tools, but they realized the same manufacturing tools could be used by this, that, and that company. So actually they decided to manufacture the manufacturing tools, if I can say that. Then the other ones were the software tools. The EDA stands for Electronic Design Automation software. Okay. So the software guy said, okay, I can do the software for this, that, and that company, not only for my company. So I get out, I do a software company, and I sell to everyone. Okay. That is disaggregation, and that happened as well with the foundries. Foundries are companies which have the machines, and they develop the processes, the epitaxial processes, the etching processes to make the circuits. And they said, okay, I can make circuits for this, and that. So actually, I can make a company that serves many, not only my company, my actual company, my current company. And that allowed the appearance of one type of company, which is called fabless company. Okay, again, we come back to the fabless term. A fabless company is a company that doesn't have in-house manufacturing capabilities, that uses tools, for instance, software provided by others, and processes provided by others to engineer a given component. Okay, I don't know, the processor in your cell phone. Okay, the processor in your cell phone can be engineered by many other companies, and they don't have their own software. They don't fabricate themselves the processor. Okay, that is a fabless company. And that brings me, if that is clear,
It's clear,
clear now?
Clear. Полегче, понятно?
Okay, more or less, fabless company. I don't own anything, and I do my component and sell it. Okay, basically. Then that brings me to the right-hand side of the slide. Okay, and you can see here the sales evolution of the IDMs, the big companies, let's say, the IDMs, and the fabless companies. Okay? So, a long time, up to, well, the graph is up to a few years ago, but it's still valid. You can see that the IDMs, the big company sales, go up and down with the telecom bubble here, make this and this and this. But the fabless company sales are always growing. Okay? This is clear from the graph. Fabless, these tiny things here, it's always growing. Actually, it is growing at a 16%, while the IDM sales is growing at a 3%, and the overall is growing at a 5%. So the IDMs are growing less than the overall, and the fabless are growing far larger than the overall. Okay? That means that the fabless way of doing things, some people is scared about the fabless way of doing things because say, okay, I don't control the manufacturing, I don't control the software. What I am controlling, okay, you are controlling your own product. I mean, you are making your own patents, your own thing, and you use tools from others. Okay, that is a risk, of course. Okay, well, so that is electronics. And if you question where is photonic integration today, today photonic integration is here. We have IDMs, many of them, but we also have foundries, fabless companies, photonic design automation tools, and of course manufacturing tool methods. Okay? So let me now, this is sort of remake of some of the slides I showed last time, and I like to use this toy analogy that you can see on the left hand side, this toy analogy, because I believe it's pretty illustrative. Basically, I bring it to make a difference between dedicated and generic manufacturing process. Okay? A dedicated process is something that allows you only to do one single thing. Okay? For instance, if you make this pass light here, you cannot make pudding. Okay? For instance, yeah, I think it can make some laughs, but that means that you can. Okay? So this is dedicated. And generic means a process where you can make small pieces, and it is at the will of yourself how you combine them to make a given functionality, okay? In this case, the Lego is a clear example. You can more or less make the helicopter, the rocket, the train, whatever, with more or less the same pieces. This happens in electronics with the transistor, the resistor, the capacitor. Okay, you combine them and you can make infinite number of circuits. In photonics, it also started to happen 10 years ago, and you can combine what we call fundamental functions, which are the waveguide, the phase shifter, the amplifier, and the polarization converter. You can combine them in what we call building blocks, which is something which is a combination of these things. Even if you can combine them in a higher abstraction level, in this case this thing here, which is a tunable laser with an amplifier, phase shifter, waveguide, and some filter. And when you combine several of all these things, you get a photonic integrated circuit. Okay? That is a generic technology. If you have only this available and you combine it to make a given functionality, we'll see this circuit later on when we talk about actual applications. Is this clear? Generic technology versus dedicated technology. Okay, fantastic. Then the next thing is how does one get the devices manufactured? There are two ways of doing it, and the names are well, the name is dedicated as well, and also shared. Okay, dedicated and shared. Dedicated means, okay, I need to fabricate my circuit. I go to a foundry and say, okay, I want to fabricate this circuit. Okay, you need to run 10 wafers. I don't run less than 10 wafers. So you need to pay for the full fabrication cost of the 10 wafers. Okay, that is fine if you have a lot of money and a clear product in mind and a winning product in the pocket. But at an earlier stage, and that also happens at education in the US. It started in the US in 1981. It followed in Europe in 1983, with MOSIS in the US and Europractice. I don't know if you've heard about Europractice. This is also something. I think it's Europractice. I see. Europractice integrated circuits. Basically, if you are doing your digital electronics project and you are developing, I don't know, some circuit, you can get it manufactured in Europractice. Okay? Because what you do is actually you don't buy a full wafer, you buy a piece of the wafer. Okay? This is your design. It comes from other universities, from other. So actually, you share the cost. That is a multi-project wafer, and that is something that since 10 years ago, we also have in photonics. So actually you don't need to pay a full run unless you are willing to. You don't need to pay it. You can get your prototypes done. Okay? The good thing about multi-project wafer is that they use the generic technologies that I have introduced, the generic technology concept that I have introduced before. And that means that there is something which is extremely important for the technologies to be successful. They need to be homogeneous. Okay, the same technology, more or less, I can say that it's used to manufacture this cell phone. It's used to manufacture your computer, and it's used to manufacture many other things, electronics, in I don't know, in washing machines, in many things. Okay, in photonics, that's not still true. Okay, there are different technologies, and there is still. We are still in the path of converging to a homogeneous technology where we can fabricate nearly all the photonic functionality that we need.
Здесь вопрос, понятно, что отличается. Мы один запуск вейфера от проектного. То есть, когда мы компании, когда мы начинаем производить что-то подобное, налаживаем все это производство, то запуск для нас тестирует, представляет труда, мы можем наши деньги. Если мы готовы создать технологии, нам выделили область, одно время, и запустить работу нет, с функциями дизайна запустить это специально. Потом уже вкладывать деньги в действие. И здесь как раз работает та же концепция, которую Паскаль только что объяснил. Используется технология университет востребованной технологии университетского цикла. Используются отдельные блоки, которые интегрируются, и на выходе вы получаете систему, да, с нужной вам функцией. Но вот эти блоки, они как стандартные элементы, как резистор, емкость, сопротивление, в обычных электронных схемах. То есть сейчас фотоника идет по пути тоже унификации.
Okay. So in this landscape, I'm going to try to describe what is actually preventing a wider use of these technologies. And but before, I just want to go through the photonic IC, photonic integrated circuit prototype development cycle. It is not different to any other engineering development cycle. Okay, basically what I did is to associate to each step the different tasks that we do in photonics. First one is project specification. Basically, you have a system concept, or not even so, you have a target functionality with given specifications. And in that stage, what you actually try to do is to try to set which are the functions that you need to perform that given specification. An example. For instance, you want to do an spectrometer. We were discussing before. So a spectrometer you can do in many different ways. But one possible way is a tunable laser and a detector, a filter and a detector. Okay. So this is one way of doing it. The other way is broadband source and a tunable filter, for instance. And depending on the specifications, you will choose of one or another way of doing things, because for instance, the tunable laser has a larger resolution, higher speed than the other one, but it's more costly because the tunable laser is expensive, the other one is cheaper but has less resolution. So it is a matter of matching the specification with the different systems that you can use to make this specification. Once you have selected the concept, then you need to decide on the on-chip architecture. And here you can see some little acronyms. Some of them are striked out, and this is specific to the photonic integrated circuit field. So basically, there are different technologies. I discussed them in October. Some of you were not here. Sorry for that. There are silicon on insulator, indium phosphide, planar light wave circuit, which is silica based, and silicon nitride. Some of the systems cannot be done in this or that technology, so you actually need to decide which technology are you going to use. In this case, I left indium phosphide there, and because you need a laser, a modulator, and a multiplexer. Okay. But these are functions. Then you need to map them to actual chip architecture. Okay, this is the optical architecture. This is the chip architecture. Because a laser can be done on chip in many ways. You can do a DFB laser, a PBR laser, Fabry-Perot laser, Moloch laser. So there are many types of lasers. Which one is the one that you require for your system concept? The same holds for the modulator and for the multiplexer. With this, you already know which are the blocks, the building blocks. I was telling before, building blocks that you need to combine in your circuit to make your functionality. Okay, so you can do already the design and the simulation. And once you are happy with this, you can make actually the blueprints, like the map of your circuit, and send it out for fabrication. Okay? In fabrication, they will get this map and turn it into a photonic into a circuit on wafers, and then later on you can do packaging and you can do test of the packaging devices. Okay. Well, you can see that one of the difficulties of all this is if you need to take care of all this, you will end up interfacing many people with different skills. You will end up talking to system guys. You will end up talking to software vendors to understand how to translate this into a design. you will end up talking or learning or discussing with scientists and physicists or engineers to learn the physics of the circuits, and you will also have to discuss with manufacturing guys, packaging guys, and testing guys, okay? So this is a risk if you want to do it smoothly, right? And that is why there are companies like ours, there are other ones as well, that help you to do a smoothly interface with all the key players in the supply chain. Okay, so...
Okay, let's do everything okay, все хорошо с вами. То есть есть некоторые шаги стандартные в процессе разработки плановых проектов. Начиная от некоторой идеи, заканчивая уже продолжая дизайном, схеме, недалеко ушли от электроники и дальше уже фокусирование производством и на уровне оптической схемы, дальше уже на уровне функциональной схемы. Все хорошо?
Good. Okay. So in the next set of slides, I'm going to present which are the roadblocks that prevent the larger adoption of this ecosystem. And this slide, you're going to see it today and tomorrow a few more times. I like it personally because I think it illustrates what we are talking about or what we are going to talk about these days. Basically, we have the photonic spectrum here, from the ultraviolet to the far infrared. You have here wavelength in microns, or you have here the wave number, which is the inverse of the wavelength in centimeters, in 1 divided centimeter. Okay, we'll talk more about this conversion in the last session tomorrow. But what I want to highlight is that depending on the wavelength, you have different applications. Okay, so applications depend on wavelength. For instance, tele and datacom, they are typically done in the near infrared. And that is because the conductor of light per excellence is the optical fiber. And the optical fiber is transparent in the near infrared. Okay, so telecom and datacom is done in the near infrared. Before I mentioned biophotonics. Biophotonics is mainly done in the visible. The reason I already gave is we are not harmed by visible light. Light visible is, let's say, compatible or harmless to our tissues, to our retina, to all our physical structure. Okay, and then there is also an interest on using wavelengths above the near infrared, as I said, because the molecules of the different substances, they have vibrations and rotations which can be clearly identified through spectroscopic techniques in those wavelengths. Okay, so this is application versus wavelength. And now the question is, if I want to do something of this with photonic integrated circuits, what do I have around? Maybe the first question is, why do I want to do this with a photonic integrated circuit? Okay, the answer to that, I think that Julian explained, the optical spectrum analyzer, is because you want to miniaturize, because you want to have portable, stable devices that you can use outside the laboratory. Okay, so if I want to use photonic integrated circuits, which technologies do I have available? Okay, I have 3-5 semiconductors, I have silicon nitride on silicon oxide, I have silicon on silicon oxide, and I have germanium silicon technologies. I have drawn these rectangles below the wavelength range where these materials are transparent, which are of use. Okay, so basically 3-5 semiconductors are mainly used in the near infrared. Silicon nitride can span from, on top of silicon oxide, can span from the visible up to 2.7, something with a gap here, depending on how you put the silicon oxide. For silicon it's the same, and germanium and silicon go up to, should we say, close to 7 microns. Okay, so if you want to do, for instance, if I ask you if you want to do sensing in the mid-infrared with a photonic integrated circuit, looking at this view graph, all of you would say, okay, I will do it with germanium and silicon. Okay, if I want to do, I don't know, biophotonics, mainly I will do it with silicon nitride. Okay, so that this view graph gives this small information, but important, small but important. But there is more on the slides. You can see people where you can go knock at the door and say, make me a photonic integrated circuit. Okay? This is a research institute in Germany, Dutch company, US companies, Dutch company, Spanish research institute, Belgium, Switzerland, blah, 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 etc., etc. But you can see that there are not so many, right? There are not so many. There are per technology. Here is one. I'm finishing. Thank you. So here is one, and here there are 7. So actually, you don't have many opportunities to shop where you want, right? So if you want to start a company and use these manufacturing services, there is a risk perception because the supplier is in a dominant position. You cannot go from this to this or to this easily. There are not 20 of them. There are just 3 or 4. So it is risky, right? So a valid question is how to increase the supplier base, because not all people which is able to manufacture photonic integrated circuits is willing to do generic technologies and multi-project. Okay, now the question. Where is? Lithium niobate does not provide, there is no foundry providing lithium niobate generic technology in a multi-project wafer as far as I know. This is only for generic multi-project wafers. Okay? But it's a good remark. Any other question or remark?
Понятно? Я на всякий случай резюмирую слайды, буду резюмировать слайды, потому что понимаете общий смысл, что то есть для каждого конкретного применения нам требуется изготовить схему, которая будет работать в заданном диапазоне длины. Для этого мы используем конкретный материал, заданный материал. На данной схеме представлено, какой материал, какие пределы длины работает и какие компании занимаются, предлагают услуги для изготовления многопроектных вейферов на данных подложках.
Почему там камера?
The same answer. The same answer was from your wait, sorry.
Okay.
Проблема заключается в том, что здесь на слайде представлены компании, которые предлагают свои технологические возможности, технологические мощности для изготовления чипов по требованию каких-то заказчиков. Наша компания занимается выпуском конкретных чипов под свои необходимости, под свои запросы, под свои потребности чаще всего и не предлагает это процесс на
студии. Okay, so increase the number of suppliers, okay? That is first message, how to increase, okay? Second message is, okay, I have clear that I need 3-5 semiconductor, okay? Let's put ourselves in the case, okay, I need 3-5 semiconductor because my specification is 3-5 semiconductor. And I go to the 3-5 semiconductor guys, these guys for instance, I said, okay, I want to make a circuit. Which are the specifications of your building blocks, okay? Your detector, which is the bandwidth of your detector. Your modulator, which is the speed of your modulator. And you start having a look to their specifications. These two guys are indium phosphide fabs. They provide multi-project wafer, they provide generic, but they don't provide even the same building blocks, and they don't have even the same specification. So actually, the fact is that if you want to do something, you end up marrying only with one, okay? And that is also, of course, a lot of risk, right? So a lot of risk, and you have less opportunity per year to develop, okay? Because multi-project wafer runs are like 2-3 per year. If you can only go to one place, you only have 2-3 opportunities. If these guys make the building blocks with the same specifications, then you have 4-6 opportunities per year, right? So that is also one thing, not only for the indium phosphide, the silicon is even worse. So yes, please make an agreement and make a detector with this bandwidth, all the same bandwidth, please. Okay, this modulator, make it with the same bandwidth. So I can shop here, here, here. more opportunities. Software is not different. Okay, this slide is for the software guys.
Sorry for interruption. Probably you need to, as I mentioned previously, you need to show this slide.
Yes.
About each slide. Introduction probably will be better.
Yes.
Short conclusion. Если вы хотите изготовить, получается, фотонную интегральную схему с какими заданными спецификациями, с какими заданными требованиями, вам необходимо работать с какой-то технологической базой конкретно. Так как каждая технологическая база, которая будет представлена в предыдущих слайдах и на этом, предлагает для запуска многопроектного вейфера одни элементы, базовые элементы с характеристиками, заданными характеристиками. На другой технологической платформе эти характеристики, эти элементы могут отличаться. Не факт, что если вы хотите изготовить, например, анализатор, примерно одной и той же схемы, не факт, что вы получите их с одинаковыми характеристиками. Именно на одной технологической платформе, на другой технологической платформе. Если дословно переводить в Паскале, вы должны жениться только с одной фабрикой. И получается, что вы не должны всегда учитывать, что вы хотите получать устройство с одними и теми же характеристиками, действительно, если там устройство по одной и той же технологии. Could you switch to previous slide?
Okay.
Excuse me, Pascal. Maybe there is any IDMs who can complain the properties of this and this supplier, or you can.
The IDMs, they have the manufacturing, so they don't complain about anything because they manufacture themselves, and they don't even tell you what they have. You don't know.
Okay.
That is for the guys as you and me that need access to something with moderate cost and to do something.
Mm-hmm.
Small companies, small research groups, which is basically the biggest part of the audience, right?
And again, as a remark, here we review different kinds of factors that limit the general application of photonic integration.
Yes, generic integration. Okay, so now if you are a designer and you want to use software to design your circuit, you are in the same trouble as before. It's the same thing but for the software. There are many software vendors. These ones are the traditional electronic vendors, electronic software vendors, Synopsys, Mentor, Cadence, which actually are currently incorporating photonic functionality in their software, right? And all these guys are pure photonic software, okay? These guys are trying to work with these guys because, of course, these have more advanced features in several things, and of course, these guys are willing to work with these guys because they don't have photonics, okay? So, but if you look at the design from a top-down perspective, basically is, I want to design starting from the system, define the circuit, design my components, make the layout, the drawings of the blueprints, the maps that I will send for fabrication, do the routing of the waveguides, verify that the layout is correct according to the rules of the manufacturer, and then get it manufactured. If you want to do all this, and you have a look at the software tools that cover the different parts, at least you need 2 software tools. Okay, at least 2. Okay, for instance, in this case, Filarete and Philips, or photon design and Philips, or numerical and Philips, or I don't know. Okay, so basically, again, you end up working with interfaces. Okay, I make my simulations in this tool, and then I export it to the other tool. I load it, and we know because we've done this many times. When you save something in one software and load it in the other, something is missing in between. And when it comes to fabricating something that costs, I don't know, 20,000 euro fabrication run, well, if something is missing in the middle, then it's dangerous. Okay?
То есть, если мы говорим о том, что История разработки фотонных интегральных схем заключается состоит из нескольких этапов. Один из них это разработка фотонных интегральных схем. Здесь используются различные программы, и при этом каждая программа обладает каким-то ограниченным набором функций. И здесь на этом слайде показывается краткая схема, какой софт какими функциями примерно обладает. То есть, если нам надо рассчитать распространение числа ключей такого рода, и нам надо рассчитать, как вся схема будет работать, то мы должны использовать как минимум 2 программных продукта, чтобы это сделать. И при этом надо быть осторожными при конвертировании данных из одной программы в другую, потому что коды иногда не совпадают, и что-то
Okay, so
we should maybe be like half an hour probably to
no, I think that they have 10 more slides.
Есть слайд, еще выдержите?
Yeah.
Easy. The day of the easy 10 slides.
Okay, fantastic. So then there is another roadblock, which is know-how. For instance, at the research group and the companies, we find very difficult to find people with all the skills required for working in this topic, right? Because despite there is a lot of training events, software vendor training, universities training, etc. This is good, this is okay, but there is a lack of a specific education in photonic integrated circuits. There are some efforts, several universities, ours among them, we provide master course, semester courses of photonic integrated circuits. But the question is how to spread them. And there is a very nice initiative, and I recommend it by a colleague, which is Lucas Proszowski, University of British Columbia. I recommend that particularly at edx.org. Okay? edx.org is a platform for massive online open courses, MOOC. Okay? There is a course on photonic integration circuits by the British Columbia University, Lucas Proszowski, which is really very good. It takes a semester, but you can learn really a lot. So that is a good online course. Of course, if you can attend some live course, that is much better always, but if you cannot, there is already one opportunity on that. Okay? Then I'll skip this one, and because it was, I was in a conference, it was more like an advertisement, so I'll skip this one. It's not important. And there is another thing which I'm sure that you are also faced with your lithium niobate and all the other chips, which is basically, if you compare, and I know when I write it here, it is not a fair comparison, it is very unfair, but I want to do it even though. If you compare these electronics and these photonic chips, well, the electronics is ready to use, right? You buy it, it is small, it is very rugged, and it is pluggable, usable, directly usable. You fit it into your cell phone, into your computer, and actually it works. But if you go to the photonic integrated circuits, then you get this. What do you do with it? With that, you can do anything, okay? It is tiny, okay? But some technologies are brittle. I mean, the indium phosphide, it falls from this gate to this gate, and it breaks in pieces. So it is really, yes, you are nodding. Okay.
We did several times.
Yeah, okay. You broke several, okay. Welcome. Welcome to the family. Okay, so, yes, and I say it's not pluggable, not usable, because you don't have fiber interfaces, you don't have RF here, okay? It is unfair because, of course, this is volumes and these are prototypes, okay? When these are not prototypes, this comparison is not true. But in an early stage where you want to get access to the technology, you would like to get access, if you are familiar with fiber optics and electronic connectors, you would be happy if your photonic integrated circuit comes in a sort of pre-packaged something, okay? And there is work ongoing, and not only by this company, but also we're doing something ourselves as well to make generic packages. As you can see, these boards here are like triangles, and you can exchange them. You can remove this one here, which is, I don't know, DC, RF. You can put all DC, all RF. You can see the photonic circuit in the middle, and you can glue a fiber here, okay? You say, no, this is happening. You don't believe it? No?
Fantastic.
This is true. This is true, huh? This is happening, okay? This is happening. Okay, so generic packaging. This is a package which can serve many circuits, as long as you adhere to the packaging guidelines. So actually, the first recommendation is when you want to design a photonic integrated circuit and you already know which is the area and the material system that you're going to use, next thing is not to design the circuit. Next thing is to think, I'm going to package the circuit, yes or no? And then if you are going to, are there templates for the positions of the fibers and the contacts for wire bonding your electric signals? If so, please use them and then later on design the intervals, okay? Okay?
Если вы, например, электронные интегральные схемы, которые, в принципе, малого размера, и могут построить систему. Наносимую на систему очень бизнес. Внутри здесь производства, в случае фотонных интегральных схем, получается кристалл. Что с этим кристаллом будете делать, не ясно. Вам надо каким-то образом с этим кристаллом общаться, управлять, снимать, выводить свет. Для этого нам необходимо его разместить в корпусе. Или либо разместить в корпусе, либо вывести электрический сигнал с помощью волокна, либо сделать, либо обеспечить электрический контакт с управляющим проводом. Фотонной интегральной схемой, конечно, и кроме того, все чипы, некоторые чипы, которые изготавливаются, на которых изготавливаются фотонные интегральные схемы, очень хрупкие. Они все эти разбивались в пыль, случайно роняя чип. Случайно роняет, поэтому требуется фокусирование. Чип различается в корпус, специально.
Okay. So next thing is about testing. Because for instance, when you get a photonic integrated circuit, sometimes the manufacturer says the propagation loss in these waveguides are like 2 dB centimeter. Okay, that's nice. How did you measure it? Oh, and then you might find different answers. Putback method, the fitting the spectral response of an MCI, Q factor of a many ways of stating propagation loss. When you go to optical fibers, then you go to the recommendation ITU G652, and there is a standard test method that tells you how everyone is going to measure the propagation loss. For photonic integrated circuit, there is no such a thing yet, and there should be such a thing. In our group, we are working on similar such a thing, and a structure that you can put on chip, and you will get the propagation loss for each mode, each polarization, but not only the propagation loss, the dispersion, the phase errors, everything. Okay?
What about coupling in and coupling out?
In this test method, the coupling in and out is not important. Okay. So you don't mind if you lose power here and here because it is a relative measurement. Okay. So, but still there is not a generic test procedure even for the propagation loss, which is something very fundamental. Okay. And then there is another roadblock for the use of these technologies. Most of these designs that you do first time, second time are unique. So actually, you go to your setup and you say, okay, I cannot measure this chip on this setup. I need to rework the setup and rebuild everything, and then you measure it, and then you take it out and say, oh, I need to measure again that one. So again, remount your lab test setup, okay? And that is a problem which is of growing concern because since there are already quite a good number, not enough, but a good number of multi-project wafer manufacturers, they even deliver more chips per run. So actually you end up with more chips that you can measure at the very end. Okay, you have like, I don't know, one run 25 chips and with, I don't know, 100 structure per chip. So you cannot measure that unless you do automation. So when to automate is also an open question, and that as I said, prevents a wider adoption of this. You can do some minor automation, but if the test methods were uniform, you could do full automation. So
in case if you have 100 elements on one line, it's
Yes, it is not.
No, it is.
It is not. Yes. Okay. So my message in this talk is and was to try to spread the generic philosophy all through the development cycle. Okay. In design, we already did at VLC. This is the slide I skipped. In fabrication processes, there are these multi-project wafer runs and new initiatives in the US and in Europe for the mid-infrared and the visible wavelengths. In packaging, unless this person here didn't believe me, there is already generic packages. No, he says no. And there is a project which is picks up, which is actually to supply a generic packaging pilot line. And in test, this is just one idea that I throw here. So, to conclude the talk or this first session, I have a set of slides which are basically statistics. I don't know if this is of interest to you. I'll go a little bit quicker through them. Basically, these statistics show the evolution of use of the multi-project wafer for different manufacturers. This is a smart photonics, indium phosphide, and they have been serving users from the industry and the academy all along the years, nearly half-half, I would say. And they get users not only from Europe, they are based in the Netherlands, as I said, but also from Asia and America. The same holds for HHI, Fraunhofer, Henry Hertz Institute, indium phosphide as well. And for IMEC in silicon photonics. So there are the same conclusions for everyone. This model of multi-project wafer runs is spreading around the use of the model of multi-project wafer runs and generic technologies is spreading around the world. This one is, for instance, VTT silicon photonics, which is a thick silicon photonics. This is Lyonics, silicon nitride. This is CNM, silicon nitride. And that's it. You've seen a lot of information. So in the meantime, while all these roadblocks are addressed, if they are going to be addressed, I don't know. Some of us, we are addressing some of them up to the extent of our possibilities. Where can you get support to get access? If you want to do a photonic integrated circuit and you don't know where to go, who can you ask? Of course, you can ask us at the Technical University of Valencia, but now we have this project together with many others that supports us to give you some advice on where to go for this and that, to invest a little amount of hours in listening to your problem, in directing you to this design house or to this manufacturer or to this technology. Okay? Of course, we are not doing the work of photonic integration companies, but we can be a pre-step. Okay, and we're doing quite well. So Pix for All project. The website is Pix for All. And yeah, as a conclusion of this part of the talk, to foster the larger adoption of PIC technologies, there are a few roadblocks to be addressed that are again listed here. We don't have enough technology offering, okay, because we only have some material systems for a given wavelength ranges. So we should somehow enlarge this offering, be a combination of a private and public initiatives. The technology platforms, they provide building blocks with different specifications. It would be great if they make an agreement, as well as for the software vendors, the same holds. For education, it would be great if we can incorporate in official education semester or even 1 year course of photonic integration, not from the perspective of the component, the circuit, etc., but from a holistic approach of the ecosystem. This generic design is something that I skipped, and the other ones refer to the test and packaging, okay, which I recommended to incorporate generic philosophy. Okay, that was for the first part. You want to add something? Is it a good moment for a break? Or?
What offer dedicated wafer run and
Not dedicated, this is share access.
share access.
Multi-project wafer.
Multi-project wafer run, and the most part of the users use multi-project wafer run.
No, they show, for instance, this one, which is quite complete. They don't give the actual number of users per run. Well, some do, okay, but they asked me not to disclose that, okay? So actually what I did is, okay, from the total number of users in that run, which part was industry and which part was academic. Because some people tend to say, oh, this MPWs and generic, this is only used by academics. That's not true, okay? Nearly half, even in some cases more than half, are industry. Okay? This is first message. Second message is, oh, this is mostly a European thing because it started in Europe, publicly funded. Not true either, okay? Also, Asia and America makes use of this. In fact, there are programs starting now in America to do these things. And they do not serve only America, I mean, they serve worldwide, as Europe does. Okay. Any other question? Yes.
10 minutes?
Yes, because the other one is
Let's
5.
Let's start 5 minutes.
Okay. Good.
Or in 10 минут или 15 минут. Давай, in 10 minutes we do this. 5 minutes before.